Hello, everybody. I'm Weizhao, a PhD student at Carnegie Mellon University. I'm very delighted today to present our paper on behalf of my collaborators, Wena, Julia, and Siwon. The title of our paper is Privacy Utility Trade-Offs in Routing Cryptocurrency over Payment Channel Networks. Excuse me. Speaking of cryptocurrency, you might immediately think of blockchain, the architecture that makes everything possible. One of the shortcomings of blockchain is its speed in processing transactions, which leads to limited scalability. To circumvent this issue, a pair of transactors can first escrow their funds on chain, second, make transactions by updating states off chain, which can be very fast, and finally, they commit their last state to the blockchain and reclaim their funds. In the abstract, we're saying they are opening, transacting over, and closing a payment channel. Multiple users can construct a graph of payment channels, which is called a payment channel network, a PCN. This is a small PCN of 5 users. We already know Alice and Bob can transact with each other via their channel AB, but what about Alice and Charlie who do not share a channel? The answer is Alice can find a path on the PCN, towards Charlie and transfer money on every hop. She chooses the green path, sends 1 Bitcoin to Bob, who forwards the money to Charlie. As a result, they update the balances of sorry, hang on, there's something wrong with the control. Okay. As a result, they update the balances of channels AB and BC. Given this core idea of PCN, people in the industry have developed the Lightning Network and the Raiden Network. Apparently, there is a belief that PCN will be a good tool to scale up cryptocurrency systems. Although it seems promising, people still have concerns about PCNs. As for us, we're particularly concerned about the transactor anonymity. Showing the balances will violate our standards, where we call it good privacy if protocol following nodes cannot link the two endpoints of transaction by simply observing the network. If we show the balances after you send money, everybody sees a path of updated balances and knows you just paid someone. So it is necessary to keep the balances secret. Here, Alice is a PCN user. For privacy, she doesn't know the balances of any channel except hers. But inevitably, the sum of the balances of each channel is public because it can be found on the public blockchain ledger. They're displayed in the middle of each channel. Let's look at how Alice would find a route on such a privacy-preserved PCN. Her goal is to send 5 Bitcoin to Charlie. She chooses the shortest green path. Now she needs to check if every hop has enough balance to send. The first hop is her sending 5 Bitcoin to Bob. She has enough money, so this hop is okay. The next hop is Bob sending Charlie. Bob checks his remaining balance. Unfortunately, he did not have enough money to give Charlie, so he has to report the bad news back to Alice. This procedure is guess and check routing. We already know it has good privacy, and we can see its bad utility from Alice's failure. Had Alice known all the true balances, she would have picked the blue route and succeed with only one trial. This is the full knowledge routing with good utility but bad privacy. Based on this, we raise a core question. Can we trade off privacy for utility by revealing noisy channel balances? We take two approaches to answer this question. First, we derive fundamental limits for privacy utility trade-offs in PCNs. Second, we design schemes whose trade-offs achieve the limits. Let me introduce our setup of the PCN model with this example. The small golden numbers are the true balances. Instead of nothing at all, everybody sees public balances, which just replace the question marks. For instance, on the AB channel, Alice and Bob um, claims to the public that they have funds of 7 against 6, while they actually have 9 against 4. Can you see the 7 against 6? Yeah. Now Alice still wants to send 5 Bitcoin to Charlie. She tries to find a path P with enough public balances on the channel she does not own. Her transaction succeeds if she can both find P and send money through it. In this example, she found the green path. From the pink circle numbers, we can tell it satisfies the first condition, and by the blue circle numbers, the second condition is also met. After confirmation, all the true balances on P are updated as on the diagram, but the public balances of only a subset of edges Q are updated truthfully. The other public balances are not updated at all. In this example, Q is a set containing the hops 1 and 3. The balances on these hops are reviewed truthfully, but those on the second hop remain as they were. In general, Q is a randomly sampled by the noise mechanism D. Now the question is, can we design noise mechanism with good privacy utility trade-off? Before answering that, we should make clear what utility and privacy precisely means. In this part, I'd like to apologize for any confusion because I'm cutting it short to make it quick. We define utility as a worst-case truthful updating probability and privacy as worst-case misestimation probability. We want them both to be as high as possible. Now that the metrics are defined, we specify the optimal target trade-off. In the presence of a baseline adversary that always guesses a node uniformly at random, our highest privacy is 1 minus 2 over n, because there are 2 correct guesses out of n total. We want to achieve a trade-off like the blue curve, where privacy is perfect whenever utility is less than 1. However, our first main result shows this is impossible in some cases. Our theorem suggests that as long as everyone always takes the shortest routes, the trade-off curves must stay in the purple area, regardless of the graph topology. The only condition in this theorem is shortest path routing, which is a weak assumption because shortest paths are favored for at least 2 reasons. First, a shortest path is easy to get from BFS if the topology is known. Second, the sender should pay a routing fee in practice to each intermediate router. Generally, shorter routes cost less. After knowing about the bound, we want to find the noise mechanism that achieves it, and we got this all or nothing noise. It is very simple. It either reviews the entire path with probability U of D, or reveal nothing at all. It is a special noise because its trade-off is always diagonal, regardless of the routing algorithm. And this is why it becomes handy when we want to adjust privacy by adjusting utility. Now let's try to break the diagonal bound. First of all, we should for sure not use shortest path routing anymore. Instead, we focus on fixed length routing on complete graphs. Besides that, we also need a different noise. This is the IID noise. It flips an independent coin for each individual edge to decide whether to update or not. And let's look at the performance of the new system. In our analysis, we have this lower bound of trade-offs under the IID noise, which is demonstrated by this figure. We plot the curves of lower bounds on different L values. We proved if n and L go to infinity, the curve converges to the perfect trade-off we wanted. However, this design has several downsides. First, there are too many channels. When the PCN is a complete graph, there won't be much need for routing. Second, it takes too much time in the worst case to find a route of fixed length. In spite of these drawbacks, our analysis still proved there is a chance to break the diagonal bound, so with further exploration, we might be able to design a more realistic system that enjoys perfect privacy utility trade-off. After discussing privacy utility trade-offs, we inspected trade-offs between privacy and success rate, which is a more natural metric. It is defined as the expected ratio of successful transactions in a sequence. We returned to the all or nothing noise and shortest path routing where we had the diagonal trade-off. We tested random transaction traffics on the Lightning Network topology and some random topologies from which we plotted this figure of privacy success rate curves. We have two main observations. First, by the shallow slopes, sacrificing privacy typically brings less gains in success rate. Second, even worse, such sacrifice can hurt success rate if privacy is already high. In the end, I want to summarize our work with a few takeaway messages. First, under shortest path routing, no scheme achieves a privacy utility trade-off better than the diagonal. Second, the privacy success rate curves do not encourage trading off a little privacy for utility. So it might be better to work at the extreme cases. Third, the diagonal bound can be broken by certain schemes whose feasibility requires further discussion. Finally, I would like to mention that these ideas are being explored by current Lightning Network implementations, such as C Lightning by Blockstream. This paper has formally confirmed that their efforts of avoiding shortest paths are going on the right track. Thank you for listening to this talk, and we hope you stay safe and healthy during the COVID-19 pandemic. Now, if you have any questions, please feel free to ask me.
Yeah, I think we have a few questions by Dara. So, yeah, if you can go.
Okay, so if we go back to how you defined privacy, it looked to me as though the definition was in terms of perfectly guessing the balances. Is that correct?
Do you need me to go back to the slide?
Yeah. Thanks.
Hang on. Okay, here it is.
Yeah. So privacy is So guessing these endpoints wrong means guessing them not exactly. Is that right?
You can imagine that when there is a transaction happening, you might observe some path traces where some edges have updated balances, and when seeing these edges, the adversary tries to guess the endpoint of the original path. He doesn't necessarily see the entire path, but he sees something, and he picks a node out of all the nodes and sees if it's the sender or the receiver.
But I mean the effective amount of privacy depends on how much noise there is, right? Because if the noise is small compared to the balances, then you don't really have privacy.
Exactly. So it's decided by the utility metric. So if the utility is 1, then you don't hide anything at all. You get 0 privacy. When the utility is 0, the best noise that achieves 0 utility is revealing nothing. Whenever a transaction happens, the adversary sees nothing, so the best he can do is to randomly guess a node.
Oh, I see. Okay.
Yeah, these are the extreme points of the utility. So
So
sorry,
the other question I had was, how do you enforce the randomness of the updates?
randomness of payments or
Your mechanism depends on randomly choosing links to reveal the balances on, right?
yes.
But in practice, you would need
You
something like a VDF or whatever, some source of randomness to enforce that. How do you expect that to be done?
we're
Sorry actually to interrupt. I think we have to really keep it
Okay,
moving.
all right.
I also had a question, so you guys can, I think, continue this offline if you so please.
Okay, no problem.
I will